Hello students, today in this video we are going to discuss the second topic of torsional vibration. It's about a two-rotor system. In the previous video we had discussed about a single rotor system. So let me start with explanation of a two-rotor system. So here in this diagram you can see there is a shaft of length L and it is having a uniform diameter D. At the two ends of the shaft, you can see there are two rotors, rotor A and rotor B, that is being mounted. And the shaft is held in bearings between the two rotors A and B. The diagram of the supports, bearing supports, are not shown in this figure. So here we will discuss how the torsional vibration will occur in such a two-rotor system. So there are two possibilities of direction of rotation of the rotors A and B. First of all, let us assume that the two rotors A and B are rotating in same direction. Then definitely there won't be any torsional vibration, because if they are rotating in same direction, no twisting or untwisting will occur along the length of the shaft. So if there is no twisting or untwisting happening in the system, it means there is no torsional vibration. Then the second possibility is, you can see here, suppose if rotor A is rotating in clockwise direction, while rotor B is rotating in counterclockwise direction. If the rotors are rotating in opposite direction, then along the length of the shaft, twisting and untwisting occurs alternately, which means torsional vibrations will occur. Now we will see one of the most important diagrams in vibration study. It is known as mode shape diagram. Here you are seeing the mode shape diagram of a two-rotor system. So when the rotors A and B are rotating in opposite direction, please look into the mode shape diagram. You can see that for a certain length of the shaft, that is LA, for a certain length of the shaft LA, you can see that the shaft is twisted in one direction, that is along this direction, while along the remaining length LB, you can see that the shaft is twisted in opposite direction. Which means torsional vibration occurs in this system. Sorry. And from the mode shape diagram, also you can see that there is the presence of a particular point called node, represented by alphabet N. What do you mean by a node in a mode shape diagram? Node is that particular point on the shaft which does not experiences any twist, which means neither clockwise nor counterclockwise motion. In other words, you can explain that node is a point whose amplitude is equal to 0. That means it remains in that particular point node will remain in equilibrium position. So here you can see that this is the node and it is located at a distance of LA from rotor A and LB from rotor B. Okay, in addition to this location of node, you can also find the amplitudes of rotor A and rotor B from the mode shape diagram. That is, here you can see that this particular height, that is CE, represents the amplitude of rotor A, while here you can see DF, which represents the amplitude of rotor B. And as you know, amplitude of rotor A and amplitude of rotor B, they are opposite in direction. Now, we will look into the basic whole idea about this mode shape diagram. So, what all information that we can extract from a mode shape diagram if we know the details of a two-rotor system? So, from a mode shape diagram, you can find, especially from the mode shape diagram of a two-rotor system, you can find the amplitude of rotor A, then the amplitude of rotor B, and you can also find the location of node if you know the values of LA and LB. So in a two-rotor system, there is a node present in between the two rotors A and B. Fine. Now we will proceed towards how to find the natural frequency of a two-rotor system and how to find this natural frequency of the two rotors, as well as how to find LA and LB in order to locate the node. For this purpose, we will draw two single rotor systems which, when combined together, will form the actual two rotor system. See, here you can see two single rotor system. This is the first single rotor system and this is the second single rotor system. You know that L is the actual length of the shaft, where this L is divided into two segments, LA and LB, where LA is the distance of node N from rotor A and LB is the distance of node N from rotor B. So please look into this two diagrams. Here you can see that. See the first single rotor system, this diagram number 1. Here you can see that the node is considered as the fixed end because, as you know, node is experiencing zero displacement. Zero displacement means it is equivalent to a fixed end. So node is considered as the fixed end, while at a distance of LA from the node, the rotor A is mounted. So this is the first system, which is a single rotor system. And on the other side, similarly, you can see that there is a second single rotor system where again node is the fixed end, and from node at a distance of LB, the rotor B is being mounted. So actually what happens here is the two rotor system is divided into two single rotor systems. Now we will look into the other details of these two single rotor systems, that is about IA, IB, which are the mass moment of inertia of rotor A and rotor B respectively. Then QA, QB, that is the torsional stiffness along length NC and length ND, which means along length NC means along this length LA, and QB, torsional stiffness along length LB. So QA is the torsional stiffness along this particular length, and QB is the torsional stiffness along this particular length LB. And finally, FNA and FNB, which are the natural frequency of rotor A in the first system, and FNB, natural frequency of rotor B in the second system. Fine. Now we will see how to find the natural frequency of a two-rotor system. The most important point to be highlighted here is that since the shaft is mounted only with two rotors, and if it has to undergo a periodic angular motion, the condition to be satisfied is both the rotors should have the same frequency, that is FNA is equal to FNB. Otherwise, you won't get a pure torsional vibration in the system. So what is FNA and FNB of a single rotor system? So FNA, you know that natural frequency of a single rotor system is 1 by 2 pi into square root of Q by I, torsional stiffness by mass moment of inertia. So if you write the equation for rotor A and for rotor B, you will easily understand that if you equate these two terms, you can replace this torsional stiffness by Gj by L, length L, according to the torsion equation. And if you are equating FNA is equal to FNB, this rigidity modulus G will cancel each other. Similarly, polar moment of inertia J will cancel each other. And you will arrive at the final equation, which is nothing but LAIA is equal to LBIB, which is actually the equation number 1. So, in order to have a torsional vibration in a two-rotor system, the essential condition to be satisfied is LAIA is equal to LBIB. Please remember this equation. Now, as we know, the entire length of the shaft capital L is divided into two segments, length LA and length LB. So definitely it is going to be LA plus LB is equal to L. That is equation number 2. Now, suppose from this equation, equation number 1, if you find LB from this equation number 1, you will get LAIA, the whole divided by IB. And if you substitute this value of LB in this equation number 2 here, then you will get the third equation, that is LA is equal to IB divided by IA plus IB, the whole into L. So these are the three important relations with which you can easily find out LA and LB. And if you know LA and LB, you can find the natural frequency of A which is equal to natural frequency of B. So this is all about a two rotor system. Now coming into a small portion within the two rotor system, and it is about the shaft whose diameters are varying along the length. Here in diagram A, you can see that the diameter of the shaft is D1 along length L1, D2 along length L2, and D3 along length L3. And here also you can see that two rotors A and B are mounted at the ends of the shaft. The only difference is that here the representation of rotors is as lumped mass. Otherwise, the problem is the diagram is same as that of the previous one. Okay. Now, if you encounter with such a shaft of varying diameters, how to convert it into an equivalent shaft? For that, you can convert this given shaft to a shaft of uniform diameter, say any one of the given diameters, which is D1. So you are converting the entire shaft into diameter D1. And if you are converting it into a uniform diameter, it is very intuitive that you will get an equivalent length equivalent length L instead of the actual length. So how to find this equivalent length L from the given diameters and the given length? So for that, you please use this relation for finding the equivalent length L if you know L1, L2, L3 and D1, D2, D3. In this expression, you can easily identify that in the brackets everywhere the numerator is D1 because you are converting the shaft to a uniform diameter of D1. It is not mandatory that you should convert the shaft to a uniform diameter D1. You can also convert it into D2 or D3, but change the equation according to that one. So using this relation, you can easily find the equivalent length and you can convert it into a shaft of diameter D1. And if you are having a shaft of uniform diameter and if there are two rotors at its ends, you know from the previous three equations how to solve it and how to find the natural frequency. Okay. So this is all about a two rotor system. So thank you for watching the video. Thank you.